Hey everyone, and welcome! Today we're diving into the incredible world of chemical reactions. And honestly, the best way to think about them is this. Chemistry is basically the universe's ultimate cookbook. And chemical reactions? Well, they're the recipes that make literally everything happen. So, let's jump right in.
Think about this for a second. We've all been there, right? You feel the incredible warmth coming off a campfire. But then you crack one of those instant cold packs and it gets shockingly chilly. They seem like total opposites. Because they are. And the reason why is tucked away inside the fascinating world of chemical energy, and we're going to uncover that secret today.
So here's our game plan. First, we're going to look at the spark of reaction, what it actually takes to get things started. Then, we'll flip through the chemical cookbook to check out the basic types of reactions. After that, we'll learn how chemists measure their ingredients, which is super cool. And finally, we'll figure out how we can predict how much stuff we can actually make.
All right, let's get into it. The spark of reaction. See, before any chemical cooking can happen, you can't just throw things together and hope for the best. There are some really basic rules that have to be followed for a reaction to even have a chance of beginning.
It all boils down to what's called collision theory, and it's basically three simple rules. First, the molecules have to actually bump into each other. Makes sense, right? But that's not enough. They also have to hit in just the right orientation, kind of like two puzzle pieces clicking together perfectly. And finally, they have to smash together with enough energy. We call this the activation energy. You know, it's like unlocking a door. You need the right key, it has to be facing the right way, and you need to apply enough force to actually turn it.
And that word, energy, is at the absolute heart of all this. Every single chemical reaction, no exceptions, involves a change in energy. It's a fundamental transaction. The reaction is either going to suck energy in from its surroundings or it's going to spit energy out. One or the other.
And here we have the two sides of that energy coin. This takes us right back to our first question. That instant cold pack? That's an endothermic reaction. It feels cold because it's literally pulling heat energy out of your hand to power itself. And the campfire? That's a classic exothermic reaction. It's releasing a ton of energy as new, more stable bonds are formed, and we feel that energy as heat.
Okay, so now that we know what it takes to get a reaction going, let's open up that chemical cookbook and look at the main recipes. You'd think there'd be millions, but it turns out that almost all reactions can be sorted into just 5 basic categories.
This table right here is pretty much the table of contents for how chemistry works. You've got synthesis, where two things combine to make one bigger thing, like making table salt. Then there's decomposition, the exact opposite, where one thing breaks apart. You've got reactions where elements swap partners, and of course, good old combustion, the one that powers your car and lets you cook dinner on a gas stove. Just about everything falls into one of these patterns.
So, how do we even know if our recipe worked? Well, chemists are like detectives. They look for clues. If you mix two clear liquids and a solid suddenly appears out of nowhere, or you see bubbles fizzing up, or there's a wild color change, or you can feel the beaker get hot or cold, boom. Those are all telltale signs that a chemical reaction has happened and you've made something totally new.
Now, any good cook knows you have to measure your ingredients just right. Well, in chemistry, it's absolutely critical. But how in the world do you measure something you can't even see, like an atom? This is where things get really clever. Let me introduce you to the mole. And nope, not the furry animal that digs up your lawn. In chemistry, a mole is just a number, a specific quantity. Think of it like this. A dozen always means 12, right? Well, a mole is just the chemist's version of a dozen. Because atoms are so ridiculously tiny, we need a really, really big number to group them together so we can actually work with them. And the mole lets us do just that, simply by weighing a sample on a scale.
And here it is. This is that magic number. It's called Avogadro's number, and it is just mind-bogglingly huge. That's 62 with 21 zeros after it. A mole of anything, carbon atoms, water molecules, grains of sand, is that many particles. It's the universal counting unit for chemistry.
So here's the key takeaway, the really crucial part. The mole is the central hub. It's the bridge that connects the world we can see and measure, like grams on a scale, to the invisible world of individual atoms and molecules. It's an unbelievably powerful tool that lets us count by weighing. Okay, this brings us to our final and maybe most practical section. We know how to start a reaction, we know how to measure the ingredients, so now for the million-dollar question. How much stuff can we actually make? This is the science of stoichiometry, and it's all about prediction.
To get our heads around this, let's just forget about chemistry for a minute and think about something way simpler. Let's say you're at a barbecue, and you're the one in charge of making the hot dogs.
So,
Here are your ingredients, or in chem speak, your reactants. You've got a package of 8 buns, but you only have 6 hot dogs. The question is dead simple. What's the maximum number of complete hot dogs you can possibly put together?
The answer, of course, is 6. You can only make 6 complete hot dogs because you're going to run out of actual hot dogs. You'll have 2 extra buns just sitting there. Your production was limited by the number of hot dogs you had.
And that right there is the entire concept of a limiting reactant. In any chemical reaction, one of your ingredients is going to get all used up before the others, and the second it's gone, the reaction screeches to a halt. In our little barbecue example, the hot dogs were the limiting reactant.
This leads us to 2 really important ideas. The theoretical yield is the perfect, on-paper calculation. In our case, 6 hot dogs. It's the absolute max you could ever hope to make. But the actual yield is what you get in the real world. You know, maybe you drop a hot dog on the ground. In a lab, maybe some of the product gets stuck to the beaker. The actual yield is almost always less than what's theoretically possible.
And this is why this is all so important. Percent yield, which is just the ratio of what you actually made versus what you could have made, is like a report card for a chemical process. For companies that make medicines or materials, a high percent yield is everything. It means less waste and more product. A low yield isn't just inefficient, it means higher costs, which can affect everything from the environment to the price you pay at the pharmacy. It's all about efficiency.
So let's end with this thought. We can perfectly predict a reaction on paper, down to the last molecule. But in the real world, whether you're baking a cake or making a life-saving drug, hitting that perfect 100% yield is practically impossible. That gap, the space between what's perfect on paper and what actually happens in reality, is where so much of the real challenge and the real genius of chemistry actually happens. Thanks for joining me today.